So what we discussed in the previous class was to identify the presence of outliers in the data. We have the residuals. But because residuals are themselves not scaled, so you never get to know if a value of 4 point something is it big enough to call the corresponding value an outlier or not. So we said that before we use the residuals to judge if the corresponding value is an outlier or not, we should scale the residuals, mobiles in the pockets. And we defined three scaling methods for the residuals. One of them was DI, which is EI over the square root of MSE. The second one was Ri, which was EI over MSE times 1 minus HII square root. And the third one was TI, and this was EI over deleted MSE times 1 minus HII, where this deleted MSE, again, if you're interested, I can give you the derivation. This is n minus k minus 1 times MSE minus EI square over 1 minus HII whole divided by n minus k minus 2. Why n minus k minus 2? It is basically n minus k minus 1, but because you are deleting one observation, your new n is now n minus 1. You are losing one observation. This is based on n minus 1 observations. So it is basically n minus 1 minus k minus another 1. Once we have these methods, did we apply them on Excel? Let us do that again, and we try to implement all of these on Excel on the delivery time data. If I have saved, we will just see them. The computation is fairly easy. You just have to implement the formulas, and you have to correctly make use of the dollar signs here and there to use the drag option of Excel. Yeah, we did calculate them. We did calculate them. We have this data on delivery time and number of cases and distance. We obtained y hat after fitting the model. We got EIs. Now look, for this EI, the first observation, the error is minus 5 point something. It is big enough, but relatively we don't know if it is big enough to be called an outlier or not. We need to divide it by the standard deviation, the square root of MSE, or advanced versions of standard deviation. Now you see, when we do divide and when we rescale, this becomes minus 1.5 or minus 1.6 or minus 1.6, which is not big enough. So the first value was not declared as an outlier. Which value was declared as an outlier was the ninth value, the one I highlighted. Now for this value, x1 is 30, x2 is 1460, and the corresponding y hat is 71 point something. Now for this value, the usual DI is the first scaling method did not detect it. It was 2.27, and usually for standardized variables, our cutoff points are -3 and +3. So DI failed to detect it. RI, on the other hand, was able to detect it because RI went beyond 3 point something. And TI very clearly detected this point. If we look at TI, there is no other value that more than the first method failed to detect it. Now that we are not going to delete it, but sensibly what we should do is we should delete this value from the data before going further towards the more assumptions. I should get rid of this row. But let us say once you are done with this phase of screening the outliers, the next thing to do is this. The next thing to do is called residual analysis. You need to analyze the residual to check if there is some serious violation of the four assumptions or not. And the residual analysis, we will start with the most popular normal probability plot, which is used for testing the assumption number 3. So I will start with normal probability plot. And for all the plots, I will be using RIs. The middle ones, RIs for creating the plots. Normal probability plot, it is sometimes also called normal QQ plot. Why it is called QQ plot? Because what we do in this plot is we plot the sample quantiles against population quantiles. Quantiles is kind of percentile. So on x-axis you have theoretical percentiles, on y-axis you have sample quantiles, and if they are equal to each other, you expect a 45 degrees line. If they are not equal to each other, you expect them to deviate from this 45 degrees line. And if they deviate from the 45 degrees line, this is an indication that the sample values are far away from normal distribution. Now, the idea of this normal probability plot, I will explain this idea with the help of a very small data. Let us say I have this data. So I'll not arrange it. Let me arrange and give you unarranged data. 2, 10, 5, 7. Let's say these are the 4 values. Usually 4 values are not enough to judge the normality, but I'm just going to explain the algorithm to you. Suppose you have these 4 values of x, and you want to see if they deviate from normality or not. The first thing you do is you sort them. You see where is the minimum, the second minimum, and so on. So find the sorted x. You get 2, you get 5, you get 7, and you get 10. So this is the sorted x. Step 1. Clear? Once you sort x's, the sorting is done just to see that what is the position of this value in the sample. Like 2 is the smallest value in the sample. To see the position of this 2 in the sample, we do the sorting. 5 is a value below which there are 2 observations. Now, my question to you is, what percent of the values in sample are less than or equal to 2? What percent of the values in sample are less than or equal to 2? 25%? I should write it as if I is the sample the value number 1, 2, 3, 4, I should write it as I over n. Is it? Where n is 4. Clear? Let me write it like this. 1 over 4. 25% of the values are less than or equal to 2. What percent of the values are less than equal to 5? 50%. 2 over 4. What percent are less than or equal to 7? 3 over 4 and 4 over 4. Correct? It's the same column sorted. They are same numbers 2, 5, 7, and 10. Just sorted, ascending order, to see what proportion of the data in sample is below this value. Now, in your sample, what percent of the data is below 2? 25%. What percent of the data is below 5? 50%. What percent of the data is below 7? 75%. And what percent of the data is below 10? 100%. Correct. Now here, when you do the try to find the position of every value in the sample with this method, there are two problems. Problem number one, I will explain it here. What is a normal distribution? When you are comparing this with the normal distribution, is normal distribution a discrete distribution or continuous distribution? Continuous distribution. Clear? And what distribution this seems like? The numbers are like discrete, right? What do you do when you convert discrete to continuous? You do a correction. What is that correction called? When you have the question from binomial distribution and you try to approximate the probability using the normal distribution, you do a correction in between. What is that called? Have you heard of this thing? The continuity correction, which is plus or minus 0.5 depending upon the sign, which direction of the probability you're trying to find. Have you seen this thing before? When you convert from discrete to continuous, you do the continuity correction. The spirit behind continuity correction, I will not go into that one, because for a discrete random variable, you have 2 and you have 3. In between, there is a patch which is missing, correct? What is the magnitude of this patch? 1. From 2 to 3, the magnitude of the patch between 2 and 3 is what? It's 1, right? So what you do is you assign half of this patch to the right side, half of this patch to the left side. So now your 2 becomes all the way from 1.5 to 2.5. This is whole 2. 3 is no more 3 now. 3 is from 2.5 all the way up to 3.5. The whole patch becomes 3. So you depend on what type of question is it, and then you decide whether to add 0.5 or subtract 0.5. You go either left or right from the required number. Exactly on the same pattern. The problem here is that the data is discrete and we're trying to compare it with the normal distribution. We should do the continuity correction here. So I should subtract 0.5 from all of these numbers here. This is one of the reasons to subtract 0.5 is the continuity correction. The second reason I will get to know when I compare it with the normal quantiles.
So why did you support
Because what you are looking at here is less than or equal to. You are looking at less than or equal to probability. When I give you the second reason, you will get to understand this point further. Now,
why do we
not from the probability, we're subtracting it from position 1.
add to the 2.5, so it be any value less than 0.5.
No, don't think it like that. Don't think it like that. Just wait for it. Wait for it. Just wait for it. Think of it like this at the moment. Think of it like this at the moment. Okay. Now, 25% of the data is less than or equal to 2, 50% is less than equal to 5, 75% is less than equal to 7, and 100% is less than equal to 10. What is the mean of the data? Can anyone calculate and let me know? 2 plus 5 plus 7 plus 10 over 4. 6. What is the standard deviation of the data or the variance? Let's say 37. 3.37. Now what I'm going to do is I'm going to obtain a value from the normal distribution with mean 6 and standard deviation 3.36 such that the area below that value is this 25%. Go to the normal distribution. This is the 25th percentile of the normal distribution with mean 6 and variance 3.37 square. And check what is the value in original normal distribution such that the lower tail area is 25%. So that is basically the percentile of normal distribution. There is a very easy way to get to this percentile of normal distribution. The command is norm inverse. So let me enter the data here. I have X, which is 2, 5, 7, 10. And then I have the position 1, 2, 3, 4. And I divided by N equals this over 4, 25%. And I need the value from the normal distribution. So I'll go to norm inverse. This should be the probability 0.25. The mean should be the mean of the data, which you said it is 6. I'll calculate it directly from the data. Standard deviation will come from the data also. So if I go to the normal distribution with mean 6 and standard deviation 3.37, I have a value 3.729 such that the lower tail probability is 25%. Does this 3.72 match with this too? We don't know. Maybe close, maybe not close. We cannot judge it by the distance. And we will do the same with all the 4 values. Now look what happens for the last value. Why did this happen? Why did this happen? Is there a value in the normal distribution such that the lower tail area is 100%? What is that value? It's infinity, right? Because there is no right tail of the normal distribution. There is no left tail of the normal distribution. They keep going until you reach infinity. This happened because this column was biased upwards. Because of no continuity correction, this column was biased upwards. When we do the continuity correction, this column will not be biased upwards because we included this value. We included this value completely in this one. Half of it should have been before it, half of it should have been after it. We included all of it into this one. The continuity correction, you will see when I do that, it will take care of the issue. Don't look at the last column, just look at this thing. And you will see it will become symmetric. When I do the continuity correction, this thing will become symmetric. This is the first value in the data. This is the last value in the data. Do you see these 2 points are symmetric and more reasonable now? 0.125 from the left side, 0.875 from the right side. Are they more symmetric? What is the area below this value? It should be the same as the area above this value. Because this is the first value in the data. This is the last value in the data, correct? It is 0.125, this is 0.125. More symmetric now. These two are the middle values, right? The area below 5 should be equal to the area above 7, which was not the case before continuity correction. Now it is the case after continuity correction. The area below 5 is 0.375, right? The area above 7 is also 0.375 above, which is 1 minus 0.625. So after continuity correction, you will get to see that you get more realistic probabilities. More realistic probabilities in terms of the symmetry of small samples. Yes. Okay. I said don't look at column B. Now look at column B. Now in the normal distribution, we expect the 12.5th percentile to be 2.12. We expect 37.5th percentile to be 4.9 something. We expect 62.5th percentile to be 7.07. And we expect the 87.5th percentile to be 9.87. Now I want you to compare column B and column D. These are the observed values. These are the expected values. If the data are from normal distribution, are they close enough? You can't tell. That you need to plot them, visually plot them. If you visually plot them and these two columns are equal to each other, what do you expect? You expect a 45 degrees line. When x is equal to y, if one of them is at x-axis, the other one is at y-axis, and you expect them to be equal to each other, they will never be exactly equal, they will be approximately. If you expect them to be equal to each other, you expect them to follow along a 45 degrees straight line. Ideally, if the data was from normal distribution, ideally my first value should have been 2.127. Ideally. If my data was really from exact normal distribution with mean 6 and standard deviation 3.37, my second value should have been 4.92. My third value should have been 7.07. My fourth value should have been 9.87. And what I observed are slightly different, right? They can be slightly different, they can be dramatically different. So if they are slightly different, we will conclude that the data is not far from normal. If they are dramatically different, we will conclude that the data are far from normal. Now, how to plot this one, call this one theoretical quantile and call this one sample quantile. Select these two. Select these two and insert a scatter plot. Insert a scatter plot. You see the scatter plot? We don't know yet until I compare it with a 45-degree line. And now I'm going to put a 45-degree line into the plot. By right click, select data and add another line here. Add another line where the x-axis and y-axis are both theoretical quantiles. Both theoretical quantiles. And then which one is the new one? The orange one is new?
Yes.
So let me double click on the orange one and change it from dots to line. This is the line I expect. Red line is the expected line. And blue dots are the observed dots. Yes. No, the blue dots are, they have the x-axis TQ and y-axis is SQ. And the red ones are TQ against TQ. Red is what we expect. Blue is what we observe. If the observed is close to the expected, the resulting distribution is not significant from the expected distribution. If they are different, then the distribution is different. Now I'm going to show you some of the popular patterns of normal probability plot. And before I go into that one, there is a caution for drawing conclusion about the normal probability plot. You need a minimum sample size of 20. Below 20, you cannot draw valid conclusions. Below 20, normal probability plot doesn't make sense. I used 4 just to explain the procedure, but with a sample size of 4, you don't expect the points to deviate from the line. You don't expect. If you have 2 points and you draw the line between the 2 points, What do you expect? Each point to fall on the line, or the point can fall here and there? On the line. What will be R square of the regression? 100%. Always 100%. So if you have a limited data of only 2 points, does that mean that the correlation between the two variables is 1?
No.
You will get 1 because of the limitation of the data. Now here, this is giving you an impression that the data is very close to normal. Why? Because the limitation of the data. Now I'm going to get more data. What I'm going to do is I'm going to select the sample of size, let us say 25. 25 here. And where do I take the data from? I will take the data from normal distribution so that I know that the data are coming from normal distribution. So I draw from normal distribution with mean, let us say 10 and standard deviation 2. So here are my values. Let me round them to 1 decimal. So I have these 25 values and I deliberately generated them from normal distribution so that you get to see the shape of a normal probability plot when the data are actually normal. This is the observed sample. Assume this is the observed sample. What is the first thing we do? Sort. So sample quantile is the sorted data. So what I do is I sort them. Sorting index is ascending order. So I sorted them. 6.3 comes at the bottom, then 7, 7.9, 7.9, 7.9, 8.1, and so on. Then I find what? I minus half over n, the position of each value in the sample. So this will be I is 1 minus half over 25. And then I find the theoretical quantile from the normal distribution. So normal's inverse and the probability should be this, mean should be 10. I'm comparing with normal distribution with mean 10 and standard deviation. Where did I draw from? 2. So if the data are really from the normal distribution, I expect the first value to be 5.89, whereas the observed was 5.5. Which numbers? Because every time it's changing. I can fix it if I want. So here are the theoretical quantiles, right? So what I do is I bring the sample quantiles close to theoretical and I select the 2 of them and plot them onto a chart. Now this is my normal probability plot where I add a new series where the theoretical quantiles are equal to theoretical quantiles. This is my expectation. Let me make it a line. And let me restrict the x-axis from, let us say, 5. Yeah. Also, let me restrict the y-axis from 4. Okay, now here is the plot. Here is the plot. A new data. Look at the points. The red line will not change. Every time I press delete, Excel will generate a new data set of 25 observations. Look at the observations. Where are they? Moving around the red line, correct? Close to the red line. 95% of the times. Close to the red line. Close to the red line. Correct? Now my question is, what if I change the distribution from where I'm drawing the data? Here, instead of normal, what if I make it gamma distribution? I take numbers from gamma distribution. With some specific parameters. And I use the average of my sample. And I use standard deviation also from the sample to compare it with the theoretical files. Now there is a problem with what? With the x's auto. X's auto. Here is the plot. Look at the plot. Do you see a systematic deviation from the red line? Systematic, not the random deviation. Previously, when the data was actually from the normal distribution, the points were deviating from the line, but they were randomly, sometimes above the line, sometimes below the line. You cannot predict whether the points. Now there you will see a systematic deviation that many points will be above the line at the start. In the middle, the points will be below the line. At the end, the points will be again above the line. See, when I generate new data every time, you will see this deviation from the line will be systematic and not random. Every time the lowest few value will be above the line, highest few value will also be above the line, and middle 50% of the values will be below the line. Look at this systematic deviation from the red line. This indicates that the data are not from the normal distribution. So if you see the points are deviating systematically from the red line, you conclude that the data are far from normal distribution, and in that case, whatever inference you are doing will no longer be valid. All the hypothesis tests you developed, they were under the assumption that epsilon follows a normal distribution. True? So if epsilon is not normal, y is not normal. If y is not normal, beta hat is not normal. If beta hats are not normal, none of the t-test, f-tests are applied. So this is a very crucial assumption in context of hypothesis testing. Any question from the normal probability plot? You will see a pattern of points above the line, then a pattern of points below the line, and a pattern of points above the line again. It's a pattern. Look how many points. 1, 2, 3, 4, 5. First 5 blue points are above the line. Then there is a bunch of points below the line.
That's fine.
There are. You don't have to find, you have to see. From this point all the way up to this point, second last point, all of the blue points are below the red line. You see it or not? Look at the first 5 points. This one all the way up to this one. Are they all above the line? Yes. Then look at from 6 all the way up to the second last. All of them are below the line. And then at the end again above the line. This is systematic. This is a pattern. If I draw the data from real normal distribution instead of gamma here, the deviation will not be systematic. Look here. The points are still deviating from the line, but is the deviation systematic? You don't know if the next point will be above the line or below the line. Can you predict? If I start from here and start going rightwards, and I stop anywhere in the middle, let's say at this point here in the middle, and I don't give the access to the points on the right, can you predict next point will be above the line or below the line? You cannot, because the deviation is not systematic. Unlike from gamma distribution, you knew the first 6, 7, 8 points were above the line, then a bunch of points would be below the line, and then again a bunch of points will be above the line.
We see this because we saw multiple graphs, but in case of real world, we will see only one graph.
You will see only one graph, yes. In real world, you will see only one graph, and you'll have to judge it by one graph, whether the deviation is systematic or not. And again, this leads us to one conclusion, that this is a subjective approach. The approach of normal probability plot is subjective. For this specific plot, I may say that the data is not far from normal. You may say it is far from normal. For me, this much deviation is good enough to judge that this is far from normal. I may say this is not big enough. So let's conclude. So it is subjective. It is subjective. There is no doubt it is not subjective. The plots are all subjective. This is very fairly close. These are very, very close. Let us say this one. One may say that these few points and these few points are far away from the line. For them, they may be far away. For me, I will say this is not far away. So it is subjective. I may come up with normality and you may come up with non-normality.
Don't we have a?
We have a test, a well-known test for normality also. I'll give you the concept of that test. It's not included in your syllabus. What that test does is that test takes the difference between this point and the line here and squares this distance, takes the distance of this point from this line and squares that distance, and takes the distance of each point from the line, squares that distance, and takes the sum. And then they derive the distribution of the sum of squares of distances from the points and the line, and they compare it with the critical value from the distribution. If this critical, the value of observed sample is big enough, more than critical value, you come up with the conclusion that it's not normal. If it is within the critical value, yeah, it's more like not sum of squares of error, it's more like sum of squares of distances of errors from the exact normal distribution. So if you do that, you will get the exact same value for the test statistic. If I do that, I will get the exact same value for the test statistic. We will both go to the critical value table of that test. We'll get the same critical value. So if two of us perform this test 100 times, we will come up with the same conclusion 100 times, given we have the same alpha, same significance level. So that approach is not subjective. This one is subjective. In the next class, we will talk about the remaining, where are the assumptions? Remaining 3 assumptions. We have 2 more charts, 2 more plots to cover the remaining 3 assumptions. One of them is called residual plots. The other one is called time series plot. So we will talk about those, and we will get done with this chapter maybe in the next class. If you have any questions, you can ask, otherwise you're free to leave.
I mean, so, the gamma distribution, is it seasonal? For example, if you have like a
No,
1,000
it's not seasonal trend.
on the
The gamma distribution is a positively skewed distribution. Where, don't go into the detail.
No, but
Confuse me more.
I'm just curious.
It has nothing to do with the seasonal trend.
No, but I mean, in the sense of the serial. Around the red line, is it systematic like that, or just the rest of the points goes?
Systematic means that some points were above the line, a bunch of points, then a bunch of points below, and then above again. This only one time.
Only one. It's a U shape, yeah.